Alright guys, we're doing some trigonometric integrals today, and I've mentioned before a very important skill in integration is to be able to look at an integral and determine quite quickly whether it's easy to do or not. Right? And by easy, I don't mean you can do it quickly. What I mean is you know you've got the tools to be able to solve it, and you're very confident that you can do it, even if it will take a while. Right? And the idea behind today's work is to try and use almost everything you know about trigonometric identities and properties to convert integrals that might look hard at first into ones that are easier to deal with and easier to manage. So I'm going to put up a bunch of facts that you just sort of know about trig, right? And this won't be everything you know, but I'll put up a bunch of them and I'll try and illustrate how you want to be thinking about these facts in the context of integration. Because I'm sure you know these already, you probably know why they're true, I hope you know why they're true, but what we want to think about is how do these facts help us integrate and help us turn maybe hard integrals into easy integrals, okay? The first thing we've got is a bunch of derivatives. Now, why are they useful? Because whenever you make a substitution in integration, I always talk about it as you have to pay what's in the yellow box. Right, you have to divide off the derivative to make the substitution, right? And so you have to lose one of those terms in the yellow box in order to properly perform the u substitution, right? And this might be a bit annoying at times. Sometimes you want to substitute, but you can't because you don't have that thing in the yellow box, and so you can't make your payment, and so you can't do it. But maybe start thinking of this as a way to get rid of maybe an unwanted term, or to get rid of a term in your integral, because you know that you can lose one of those things in the yellow box when you're making the substitution. So think about how that can be used actually to your advantage. Okay, we'll see examples of this soon, but keep that in mind. All right, the next one is the double angle formulas. I hope you can see the stuff in the orange box is easy to integrate because a 2x is easy to deal with. Whereas the stuff in the pink box, when you just look at that, might be a bit harder to deal with, okay? Because maybe you don't have the payment that you can make. Now, the top one, you probably can do it quite easily, but the bottom one might be a bit harder, all right? And so what this tells you is that any quadratic sine or cosine term is actually easy to integrate by converting it into a cos 2x. Okay, so cos squares and sine squares by themselves would be quite hard, but by converting them to cos 2x, they become pretty easy. All right, and the last one. This doesn't give you an easy way out, but what this does tell you is you can easily switch between sine squared x and cos squared x. Okay, and where that might be useful is if you've done a substitution, say you've put in u equals sine x, and you've got a bunch of coses in there, maybe you can convert the coses into sines by using this green box. Okay, so keep those things in mind, and of course the other related ones like the relationship between tan and sec and those sorts of things as well. Okay, they give you ways of switching between those different functions, which might be used to your advantage. All right, so here's an example. I'm going to try and illustrate what goes through my head as we do this. So I would look at each term separately and think about what I can do with them. So start with the sine cubed x. What I'd be thinking is, well, there's 3 copies of sine x in there. All right, I can lose one of them by paying it and substituting u equals cos x, because the derivative of cos is negative sine, but forget the negative, right? It's a way to get rid of one of those copies of sine x. And so we can then transform the remaining sine squared into cos squared using the green box from previous, right? And so that way, that's probably quite the best way to deal with that one, right? Whereas sec squared, well, I've got a bunch of options for sec squared. I can maybe get rid of that by substituting u equals tan x. I can always transform sec squares into tan squares, but also, I know that sec squared is just made of cos as well, because sec x is 1 over cos x. So I've got options there. Which one do I take? Well, if I compare the yellow bubble with the blue bubble, I see maybe the first two aren't very helpful, because if my other term involved tan and I had a way to deal with tan, maybe I'd go that way. But if everything in the blue bubble is telling me that I can easily work with cos x, maybe I just leave sec squared as 1 over cos squared. Okay, and that's how I think about these things. Alright, so let's try that. The plan then is to substitute u equals cos x, transform the sine squared into cos squared, and then just think of the sec squared as 1 over cos squared x. Okay, so off we go. I will then put u equals cos x, du is negative sine x dx. Better deal with my limits as well while I'm there. When x is 0, u is cos 0, which is 1. When x is pi on 3, u is cos pi on 3, which is a half. Okay. Alright, I think of my integral now as this. What I've done there is I've split my sine cubed into the yellow sine squared and the blue sine x. I've chucked a negative there, and so I've got a negative outside as well. I've done that so that I can easily see where du will go. The whole blue part turns into du. What I do with the yellow part, what I do with the sine squared, I change it to 1 minus cos squared. What I do with the sec squared, I think of it as 1 over cos squared. So that's what it's going to look like, right? And of course, all the cos x's turn into the u, and so actually, the top is 1 minus u squared, and the bottom's just u squared. And then now I can split the fraction, so I get that, and I can integrate that quite easily. Alright, and then I just evaluate those things, and I get a half from there. Okay, and so that's how I think about that. I would think about my options and think about the best way or the best options to choose that will make the whole thing easier to solve. Okay. All right, here's another thing we can use. These ones are ways of turning products into sums, right? Because individual sine or individual cos terms are easy to integrate. Maybe a product is quite difficult. Okay, so we can change products to sums. Now, do we have to remember these things? Well, probably not. I'm not sure if you've seen them before, but I wouldn't remember them. I would remember that it's possible to change products to sums, but this is something that I think I would just work out on the spot, right? I reckon the less to memorize, the better in maths, so I would remember that it's possible to change products to sums, but I wouldn't memorize these. Rather, what I'd do is I would take these ones, which hopefully you have memorized, and observe that if I need to work with a mixture of sine and cos, I would be looking at sine A plus B, because that one involves a mixture of sine A cos B, cos A sine B, right? But if I'm thinking about a pure sine or a pure cos, like cos A cos B or sine A sine B, I'm going to build that using a cosine, right? I would do it that way. And that might be a bit confusing at first, but let me show you an example. Hopefully it makes it clear. Say we want to integrate this guy. This is a mixture of sine and cos, right? So pretend we didn't know anything I just said in that slide just before. Pretend we were going at this sort of blind. This is a mixture of sine and cos. And so I would just think about sine A plus B, because I know that the sine one gives me that mixture between sine and cos, right? And so I would look at this one and say, well, if I change the plus to a minus on the left-hand side, not a lot changes, only the plus changes to a minus. And so it's almost like simultaneous equations, where if I add these two together, right, the terms on the right disappear, right, and then we actually recover the identity we saw on the previous slide. Okay, so you want to look at that a bit slower yourself, right? But the idea is when I see a mixture between sine and cos, I know that a sine A plus B identity will tell me something about that sort of mixture, that sort of product. Okay? And so I simplify that, I get this. That sine 3x cos x is actually half of sine 4x plus sine 2x. Okay, and so let's use that and see what happens when we integrate that instead, because I think this should turn out a lot easier. Right, to integrate sine 4x, you just need to divide by 4. To integrate sine 2x, you just divide by 2. Sines become negative cos, and so that's what you get. Simplify, and we're done. Okay, so if you have a sort of product of sine something cos something, or both sine or both cos, you can convert that to a sum by using the appropriate identity. Okay, for a mixture of sine and cos, use sine a plus b. For a sine or a cos, use cos a plus b. Alright, so that's another trick we've got. The final one. This is the trick we use if we have exhausted all other options and we're tired and we're done and we're angry and this is the very last thing we can try. We use a t substitution. Alright, there's nothing better to do. We're going to use one of these ones. Alright, you should hopefully know from your other course that if you put t equals tan x on 2, you have these three expressions for sine x, cos x, and tan x. Of course, the advantage of these is they are rational expressions, like fractions of polynomials, and we've done a lot of work with integrating those ones. We've got tools like partial fractions, we can use the f dash over f, all those sorts of things, and yeah, that's worth a shot if you've got nothing better to try, okay? But of course, when you make that substitution, you've got to see what it does to the dx and the dt and stuff, so let's differentiate that. We get dt dx equals half sec squared x on 2, which actually, conveniently, sec squared can turn into 1 plus tan squared. Which is good, because 1 plus tan squared x on 2 is just 1 plus t squared. So we get 1 plus t squared over 2, which means that dt can be written as t squared plus 1 over 2 dx, and so dx can be written as 2 over 1 plus t squared dt. Now, why that last one is helpful, right, is that dx can always transform into dt quite easily. You don't need to look for anything to pay. You don't have to lose any particular term that's got to already be there to make this substitution. You can just do it. Okay, so dx equals 2 over 1 plus t squared. dt is something that we will use. So, something like this, where you would just be stuck if you tried anything else, maybe. There might be some clever way to do it, but let's just try this. Alright, so what's relevant from the previous slide? The relevant stuff is that cos x equals 1 minus t squared over 1 plus t squared, and that dx dt thing that we just did. Now, in practice, you would probably want to show your working, actually differentiate t equals tan x on 2, and do it all out every single time, okay? Because you need to show where you got that from. But we just did that, so let's just put it in. So the integral will be this, where we've just replaced the cos x with 1 minus t squared over 1 plus t squared, and we've done our dx substitution there. When we multiply those denominators, the 1 plus t squared from doing the substitution will cancel with the 1 plus t squared from the cos, right? And so it actually simplifies quite nicely into this, all right? Make sure you understand how that expansion works there, but the t squares actually cancel, leaving you with 2 over 1 plus 1, which is 2, and that's just going to be 1. And so your integral is just t, which is just tan x on 2, right? And so that's your last trick if everything else fails. Okay, thanks for watching, and I will see you next time.